Okay, so today we're diving into something pretty cool, I think. How certain drugs, those antibiotics we hear about, well, they manage to take out bacteria like it's nobody's business, and they do it by targeting the bacterial cell wall. We've got some really interesting stuff to work with today, an overview that lays out the whole process, a diagram that shows us visually where these drugs do their thing, and, a whole table packed with examples of these cell wall attacking antibiotics.
Right.
So our mission, if you will, is to understand, why this bacterial cell wall is such a weakness and how these drugs are so effective at exploiting that weakness.
Yeah, absolutely. So to kind of kick things off, maybe we should start with the bacterial cell wall itself, right, for everyone listening. Um, Imagine a bacterium, right? Unlike our own cells,
Yeah.
these little guys are surrounded by this really strong outer layer,
Right.
right? The key player here is what we call peptidoglycan.
Okay.
It's this really unique net-like material that makes up this outer layer. You can think of it like armor surrounding the entire bacterial cell.
Okay, so this armor, this peptidoglycan, what does it actually do for the bacteria? I mean, why is it so important?
Well, it's vital for a couple of big reasons. First, it gives bacteria their shape, whether they're rod-shaped or spherical or even spiral-shaped. The peptidoglycan is what dictates that form, but even more crucial is its role in preventing the bacteria from literally bursting. You see, the inside of a bacterial cell has a very high internal pressure, like a balloon that's been blown up really tight.
Right.
And without this strong cell wall to counteract that pressure, the cell would just explode
Mm.
due to what we call osmotic pressure.
Wow, that's a pretty intense image.
Yeah.
So this tough peptidoglycan layer is key for keeping the bacteria in one piece. Now, this is where things get really interesting. Our own human cells don't have this peptidoglycan structure.
That's exactly right. And that is the genius behind targeting the cell wall with antibiotics. Because we don't have peptidoglycan ourselves,
Hmm.
drugs that mess with its construction can specifically target bacteria without harming our own cells.
Ah, I see. So it's like finding their Achilles heel, something they have that we don't.
Yeah, you could say that.
So we know the cell wall is crucial and unique to bacteria. Now, in our overview, it mentions that these drugs inhibit its synthesis. So can you break that down for us? What does that actually look like at the, molecular level?
Sure, so basically these drugs throw a wrench into the machinery that builds and links those peptidoglycan molecules. Remember our armor analogy?
Right.
Well, it's like trying to build that armor, but with faulty materials or broken tools.
Gotcha.
As the bacteria grow and try to multiply, they need to make more cell wall. But if you block that construction process, the existing wall gets weaker, and the bacteria becomes much more vulnerable to that internal pressure we talked about.
So they basically can't hold themselves together.
Yeah, precisely. And especially for growing bacteria, this often leads to the cell bursting open and dying.
Wow. So it's like we're catching them in the act of building and then sabotaging the whole operation. Now, our diagram shows several points where this interference can happen. Are there any targets that are particularly vulnerable or that drugs commonly go after?
Well, the cool thing is when you look at that diagram, you see that there are multiple enzymes involved in the different stages of making peptidoglycan, for instance. Some drugs target the enzymes that assemble the precursor molecules, the basic building blocks of the cell wall.
Okay.
Then you have others like penicillin that interfere with the enzymes that link those building blocks together. Those crosslinks are what give the cell wall its strength.
Mm-hmm.
So by hitting different steps in the process, we have a bunch of drugs that can be really effective.
And our table really shows that diversity, right? There are all these different classes of antibiotics, and they all target these different stages of cell wall synthesis. It's amazing how many ways there are to disrupt this one process.
Absolutely. And understanding these mechanisms is so important for developing new antibiotics and figuring out how to fight resistance. By knowing exactly where a drug attacks, we can sometimes predict how resistance might develop, and then hopefully design new drugs that can get around those resistance mechanisms.
So it's like a constant arms race.
Yeah, you could say that.
Okay, so just to recap what we've covered in our deep dive today, the bacterial cell wall is made of this unique peptidoglycan material. It's essential for keeping the bacteria alive because it provides structural support and prevents them from bursting. And because our human cells don't have this structure, it's the perfect target for antibiotics.
Right.
By interfering with the construction of this cell wall, these drugs weaken the bacteria and ultimately cause them to die, especially when they're trying to grow and divide.
Precisely. And this fundamental difference in how our cells are built is why targeting the cell wall has been such a successful strategy for treating bacterial infections.
Yeah. This has been a really fascinating look into how these drugs work now, for all of you listening out there, think about this. This cell wall is absolutely vital for bacteria, right?
Mhm.
So what would push them to develop resistance against drugs that target such a critical structure? I mean, how do you work around something so essential?
Yeah.
And then thinking beyond the cell wall itself, are there any other unique features of bacteria that we could target for the next generation of antibiotics? These are some pretty big questions to ponder. Thanks for joining us on this deep dive.
Thanks for having me.
See ya.
Bye.